Hi, in this video, I want to discuss about cross-entropy loss and try to give you a very intuitive understanding rather than just a mathematical formulation. If you have worked on machine learning or if you have discussed with people working in machine learning, you might have come across the term cross-entropy loss. The mathematical formula for cross-entropy loss is very simple, but yet I have seen that many people do not have an intuitive feel for what exactly this is. So at the end of this video, I have made three questions. And if you can answer those three questions, I myself will be answering. But if you can think about the answer without listening to what I am saying for those three questions, you can say that you have a fairly good understanding intuitively about cross entropy loss. So, first, understand that cross entropy loss is used in classification tasks, not in primarily regression tasks. In regression, mean squared error and many other ways are there to define the loss of your model. But if you have let's say, a convolutional neural network that takes an image and classifies the image into one category, then you can use cross entropy loss to define how good or how bad your model is. So take an example. Imagine this stick figure is that of an animal. And you are asking someone, not a model, you are asking a person to predict what animal this is among these four categories: dog, cat, tiger, and lion. And instead of picking one name, you are asking the person to kind of tell what is the likelihood for this stick figure to be each of these animals. And let's say you are asking this question to three people: person one, person two, and person three. Imagine that the person one answers in this kind of a distribution. They say that dog is 20% probability, cat, that stick figure is cat with a 29% probability, tiger with 31, and lion with 20. Clearly, you can see that person one is not very confident at all regarding which category or what is the stick figure image about. Person two says it is dog with 97 percentage, and the remaining 3 percentage, he says it's cat or tiger or lion. And person three says it is 97 percentage cat, and remaining percentage is distributed to dog, tiger, and lion. So these are three people, and you can see that person two and three are very confident. Person one is not very confident. But obviously, both person two and three cannot be right. Only one of them, or sometimes both of them, can be wrong. Now, imagine that this stick figure was actually that of a cat. Now you can see that person 3 is confidently right. Person 2 is confidently wrong. And person 1 is underconfident and wrong also, because person 1 has attributed highest probability to tiger. Cat has the second highest probability. So person 1 and person 2 are wrong. But person 2 is wrong in a disastrous way, because they are saying that it's a dog with 97% probability, while the image, the stick figure, is that of a cat. So how do you penalize these three cases? In one case, you have underconfident and wrong. In the second case, you have confident and wrong, confident and right. To me, confident and wrong is the worst thing to do, because you are misleading someone else. I have had people very closely associated with me say completely wrong things in a very confident manner to me, and then that has cost me a lot of time and effort, whatever. So I absolutely hate it when people say things with confidence, but they are completely wrong. So you want to penalize someone who is confident and wrong the most. You also want to penalize someone who is wrong underconfidently, but probably a little bit less. And if someone is confident and right, then you don't want to penalize them at all. And if they are 100% right, no penalty. But if they are, let's say, 98% right, 97% confident and right, you don't want to penalize them as much. So this is the idea. How do you distribute this penalty? How do you penalize appropriately? This is where cross entropy loss can help you. So in cross entropy loss, we discuss not in terms of percentage probability, but in terms of probability that ranges from 0 to 1. So first thing is, look at what the reality is and compare that with the predictions that are made by person 1, 2, and 3. So the reality in this case is that the image, the stick figure, is that of a cat. So that means that the probability distribution is something like 0% is attributed to dog, tiger, and lion, and cat is 100%. So this is the reality. And you can see that person 3 is closest to the reality. Person 2, because that person is confidently wrong, is the farthest away from the reality. And person 1 is as good as random guessing because the confidence level is very, very poor. So firstly, convert this into probabilities. So numbers between 0 and 1. So the first one, if we write it as a vector, it will be 0, 1, 0, 0, which is the reality. Person 1 is 0, 0.2, 0, 0.29, 0.31, 0.2. And person 2 is 0.97, remaining are 0, 0.01. And person 3 is 0.97 for cat, and remaining is 0.01. So our goal with cross entropy loss is to make sure that this person gets least penalty because of being confident and right. So that is the first goal. Second goal is this person should have heavy penalty because they are confident and wrong, and not so heavy penalty, but yet there has to be some proper penalty to person 1 also for being highly undecisive or highly underconfident. So how do we do that? It's very simple. Mathematically, cross entropy loss has this equation: negative sigma y log p, and the sigma is done over all the i's. So here I is from 0 to 3, or rather let's say 1, 2, 3, 4, because you have 4 animals here. So you have 4 classes which are 4 animals, and you have true labels for all the 4 animals. What are the true labels? The true label corresponding to the dog, I mean in this particular vector, the dog has a value 0, cat has 1, tiger has 0, lion has 0, because it does not matter to us whether something is a dog or tiger or lion, because here we are only looking at cat or not cat. So everything, this is like a cat means 1, everything else is 0. So here the yi is nothing but the real label associated with that animal, and p is the predicted probability that for that animal. And who is making the prediction? ML models are making the prediction. If we replace ML model with, in this case, person 1, 2, or 3, so person 1 has said that pi where I equal to 0 is 0.2, pi where I equal to 1 is 0.29, pi where I equal to 2 equal to 0.31. What about yi? Yi, which is the real label, when I equal to 0 is 0. Yi when I equal to 1 is 1. Yi when I equal to 2 is 0. So this is how it looks mathematically. So y is the real label for the ith animal, and p is the predicted label for the ith animal. Now, couple of things to note here. There is a negative sign associated with cross entropy loss. That's because here you are taking the natural logarithm of a probability, and you know that probability is less than or equal to 1, which means log of something less than or equal to 1 is a negative, is almost always negative. If it is log of 1, then it is 0. So here you can see that it's a negative number. So to make the loss value a positive number, that's why you add a negative sign. Second thing is, why are we using logarithm here? Why not something else? We are using logarithm primarily to amplify the confidently wrong answers. So let's say, let's look at an example of confidently wrong answer. So person 2 was confidently wrong. How do we say that person 2 is confidently wrong? Because the reality is that it is a cat. But person 2 is saying that there is only 0.01 percentage, 0.01 chance, which means 1% chance that it is a cat. So the person 2 is completely wrong. And that is the reason why we are using log, because if we take log of pi, let's say pi for I equal to cat, which is p cat. What is this for person 1, person 2? It will be log of natural logarithm of 0.01. And this should be a big negative number. So let's calculate what is that. Ln of 0.01. So this is a relatively big number, negative 4.6. And when you add negative sign to it, so and we know that yi for cat is 1 because the true label for cat is 1, and then you add a negative symbol. So basically, for person 2, the cross entropy loss will become minus 4.65, right? Yeah, 4.60. which will be 4.60. So the reason why we are taking logarithm is because so that numbers that are very close to 0 will be amplified, because and it's getting multiplied by yi. So here you might wonder, okay, if it is getting multiplied by yi, and because yi is 0 for dog, tiger, and lion, does it really matter what the pi for those, whatever the probability distribution for tiger, lion, and dog are? It does not matter. And that's because in this case, we don't care whether your model is saying that, okay, as long as it's saying it's 80% cat, the model does not care. We don't care whether the remaining 20% is attributed equally to tiger, dog, and lion, or let's say it's saying 20% it could be a tiger, and 0% it will be a dog, and 0% it will be a lion. We don't care about that. We only care about the cat. So that's the reason why here, although we'll end up amplifying only the prediction corresponding to cat, because yi for only the cat is 1. For other three animals, yi is 0. So essentially, we are amplifying confidently wrong answer whenever someone says confidently that this is not a cat. So that's what essentially we are doing. So now what we can do is, in cross-entropy loss, let's calculate the cross-entropy loss in each of these cases. So let's take the equation, right? So cross-entropy loss is nothing but minus sigma yi logarithm, which is natural logarithm, log e pi. Now, what is yi when I equal to dog or tiger or lion? It's 0. So we just need to consider the logarithm for probability prediction corresponding to cat. So for person 1, it will be, so I'm not even considering y now, but basically it will be negative natural logarithm of 0.29. And that will be, so this is essentially the penalty. The cross entropy loss is the penalty. So let's calculate 0.29. It's minus 1.23, minus 1.24. So this will be minus of minus, so plus 1.24. So this is the kind of penalty that person 1 gets. How much is it for person 2? That we already calculated. It's 4.60, right? And for person 3, it will be a logarithm of 0.97. This should be very small number, minus 0.03. And we take minus of minus, so it will become 0.03. So we basically achieved what we wanted to achieve. So person 3 should have given very less penalty. It is true. The penalty for person 3 is 0.03. Person 2 should be given heavy penalty. That is also true. Person 2 is given 4.60 penalty. And person 1, not so heavy penalty, but yet it should be there because underconfident, wrong. So it's 1.24. So cross entropy loss basically achieves what we wanted to achieve logically. It's a very nice mathematical formulation for achieving something that is very logical. Now I have one more thing to discuss. Cross plus entropy plus loss, right? There are 3 terms, cross and entropy and loss. What exactly is cross here? Cross for the reason that we are comparing between the probability distribution corresponding to reality and probability distribution corresponding to the predictions. So the probability distribution corresponding to reality is 0, 1, 0, 0. Because it's in reality, there is only one animal. We are saying that it's a cat. So it's 0, 1, 0, 0. But in prediction, it looks something like this. And we are comparing between these two. Entropy, because we have, it's a measure of uncertainty. And here we do have uncertainty with respect to our predictions. Our prediction will never be like saying 100% this is this animal. It's very unlikely. So we are indeed having a measure of uncertainty, and entropy is basically that. And what about loss? Loss because who is making these predictions? In our example, the people, person 1, person 2, person 3 made the predictions. In reality, in our machine learning framework, the ML models or deep learning models make this prediction. And if the deep learning model predicts a low probability for a correct class, just like how person 2 said that it's very unlikely that it's a cat, the loss should be high. We saw that the person 2 had a loss of 4.6. So if an ML model predicts a low probability for a correct class, where a probability should be close to 1, if an ML model makes a prediction close to 0, the loss should be high. So that is the third term in this cross entropy loss term, third one. Okay, now let's come to the last part of the video. I mentioned in the beginning of the video that I have 3 questions for you. Here is the first question. Let's say you have a 4-class classification, and this 4-class classification has a loss of 1.38, right? How good is the model? This is a great question. Just pause here and think about it. If you can come up with the answer to this, you can feel confident enough to have a fairly good intuitive understanding of cross entropy loss. So let's think about this, right? So if you have a ML model, let's say a very bad ML model, what will a very bad ML model do? It will do a random picking. It will randomly say that this is a cat, or this is a dog, or this is lion or tiger, which means the probability distribution for each category will be 0.25, right? Because there is equal chance that the model will pick cat or dog or lion or tiger. So it will be something very close to this if it is a very bad model. So, and this is as good as you giving an image to a 2-year-old kid, or you asking the 2-year-old kid to pick a number between, or asking a monkey to pick a number between 1 to 4, and based on that you make a prediction. So it's like as good as it's like this is what random classification or random prediction does. Now in this case, how do we calculate the loss? The true class could be either it could be 1 0 0 0, the reality, or it could be 0 1 0 0, or it could be 0 0 1 0, or 0 0 0 1. Now you are comparing these two, and the cross entropy loss in this case would be negative natural logarithm of 0.25. What is that? Let's calculate. So negative natural logarithm of 0.25 is 1.386. So if the loss is, this is equal to 1.386. So if the loss of a 4-class classification model is 1.38, it is a very, very bad model. It's a worst model because the model is as good as just randomly picking one out of the 4 classes, right? So this is how, from the loss value and from what the model is expected to do, meaning the model here is expected to do a 4-class classification. This is how you can see that it's a bad model just by looking at the loss value. So the loss is always with respect to what is the model's objective. Now let's say you have another ML model which is supposed to do a 1,000-class classification. And let's say this model also has the exact same loss of 1.38. How good is this model? So for that, let's say we had a 1,000 class classification. If the model was as good as randomly picking, what would the probability distribution for each class would be? Each of them will be 10 raised to minus 3, basically 1 by 1,000. 1 by 1,000, like etc., etc., etc. There will be 1,000 such entries. Each of them will be 10 to the minus 3. And only one of them is the true label, which means the cross entropy loss corresponding to random picking will be negative logarithm of 10 to the minus 3. This is natural logarithm. So this will be how much? Negative logarithm of 0.001. This is 6.90. So if the model was randomly picking, the cross entropy loss would have been 6.907. But in this case, the loss is 1.38, which is much lesser than on a logarithmic scale. That too, like it's not on a linear scale. On a logarithmic scale, is much less than 6.907, which means in fact this is a quite good model. So the loss for this model and this model are exactly the same. This is a good or even decent model. So this is how you can tell how good or how bad a model is by knowing how many classes it is classifying things into and what is the loss. Now, here is another question. An MNIST classifier, if you don't know what is MNIST is nothing but a data set consisting of handwritten digits from 0 to 9. So it has 10 digits. Basically, it's a 10-class classification problem. An MNIST classifier has a classification accuracy of 0.1. What might be the loss of this model? Let's think about this, right? If MNIST classifier is having a classification accuracy of 0.1, it means it is as good as random picking, because randomly, if without even looking at what the input is, if you randomly say that this is 1 or this is 0 or this is 4, you will, at the end of the day, you will end up having an accuracy of 0.1 because you're taking 1 out of 10 classes. What might be the loss of this model? It is very likely that it's not exactly sure, but it's very likely that if the accuracy of the model is very close to random picking, then the model is not doing, it has not learned anything about the images. It's making a random prediction, which means the probability distribution of the predictions that a model is making is 0.1, 0.1, etc., etc. 10 entries will be there. It will be something like this. Not exactly, but approximately. And the loss corresponding to this would be minus logarithm of natural logarithm of 0.1. And this would be what? Of 0.1 means 2.30. So the loss of this model would be close to 2.30. In all likelihood, I'm not saying it will be exactly 2.30. It can be less than 2.30 also. And you know how? If let's say, if for whatever reason, let's say classification accuracy of this model is 0.1, but let's say the loss is 2 in one case. So let's take three cases. In one case, the loss is 2. In another case, the loss is 2.30. In another case, the loss is 2.60. So these are three cases. But the classification accuracy is still, let's say, 0.1. You might be wondering, how is this possible, right? This can be possible in one way. See, in calculating the cross entropy loss, ultimately only the comparison is only coming when corresponding to the true class. So if the true class is this one, you're only taking negative logarithm of whatever this number is. If true class was this guy, you will take negative logarithm of only this number. So let's say for whatever reason, model was making slightly more confident predictions whenever the class is a correct class. So let's say you are inputting an image of of a letter 2, digit 2, and digit 2 is nothing but 0, 1, 2. So instead of it being 0.1, 0.101, and here it's, let's say, 0.3, and here it is 0.05, 0.05, etc., etc., up to 0.1, like this 10 entries. Now, if the input is 2, the real label should be 0, 0, 1, 0, 0, 0, 0, 0, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It should be something like this. But let's say the model makes a prediction such that it is slightly more confident in making the right prediction, which means the cross entropy loss in this case would be minus logarithm e of 0.3 instead of 0.1. And what is minus logarithm e of 0.3? This is 1.2. So you see, if the model is slightly confident in making right predictions, the loss will be less than 2.3. 2.3 is when the model is completely underconfident. It's not at all confident about any predictions. It's random. So if so, in that case, the loss will be close to 2.3. Accuracy is still 0.1 because accuracy is calculated over a large number of images. But if the model is slightly more confident in making right predictions, the loss will be less than 2.3. What if the model is slightly more confident in making wrong predictions? So let's say, for example, model is saying that in all likelihood, so let's say the real image that is shown is that of a 2, which means the 0, 1, 2, this one is a 1. This is the reality, right? There are 10 entries like this. And now model is saying this is 0.3, this is 0.1, this is 0.05, then 0.1, 0.1, like that. Now the comparison is coming between this and this because all the other entries are 0. So in the formula, minus yi ln pi, wherever yi is 0, which is the case with all the other, it does not matter what comes inside the logarithm. Only when yi is 1, that's where the logarithm comes into picture. So here the cross entropy loss will be minus yi is 1, right? Because for image equal to 2, the yi is 1, negative logarithm of 0.05, and that would be, this is 2.99, you see, which is greater than 2.3. So if the loss is less than 2.3, it means the model is making slightly better confident predictions, slightly more correct confident predictions. And if the loss is greater than 2.3, it means the model is making confidently wrong, even more wrong predictions confidently. So this is what you can interpret by knowing the loss of a model and what kind of classification it is trying to make. So I hope this gives you a fairly good intuition about cross entropy loss. Instead of just looking at its mathematical formula, you I hope you can now think of cross entropy loss as a measure of goodness, or as a measure of how good the model is. And these calculations, if you cannot fully wrap your mind around this, just go through it once again. I'm sure you can understand it if you do the calculation yourself once with hand. But with that, I think we can stop this video here. Thank you so much for listening, and we'll see you again in the next video. Take care until then. Bye.